In this video, we do section 4b again. We continue with that, power of compounding. We'll do several problems related to simple and compound interest. So in problem 3, read the question, and if you need to pause the video, do that. 15,000 is borrowed, so that's $15,000. The annual percentage rate is 6.5%, so R is 0.065. The important thing to notice is it's compounding. Somewhere in the question, you'll need to see whether it's compounded interest or simple interest. It's daily compounding, so it tells us the number of times that it is compounded is 365. What we need to figure out is the amount. So what is the amount when the time is 6 years? So it's given in years, so we don't have to worry about it. So clearly it's a compound interest formula where you need to figure out A. So A is P times 1 plus R over N whole to the NT. We plug in all the numbers carefully into the formula and we enter all the numbers into the calculator. Make sure you're entering everything along with parentheses. Hit the enter button once and get your final answer. So what I'm trying to say is don't do the calculations in bits and pieces, because every time we do a certain calculation, we might tend to round it to the second decimal place. And if you do multiple roundings in a calculation, then your final answer may be off by a significant amount. So make sure you're not doing the calculations in pieces. Just enter it all into the calculator once along with the parentheses and get a final answer. Make sure you do this and see for yourself if you're getting the same answer as I did. Now the next problem, again, if you want to pause the video, just do so that way you clearly understand the question before you start working on the details. So the question starts off with how much money should be deposited. So basically, the amount deposited is called the present value, or P. So P is what? So how much would you deposit today that in an account that earns an interest of 10.5%? So 10.5% is 0.105. We need to figure out if it's compounded interest, then we need to find out how many times it is compounded. So we have n equals 12 because monthly would mean 12 times a year. If the final amount or the accumulated amount is 22,000 for a period of 4 years. So make sure that the time is in years. Now, A equals P times 1 plus R over N whole to the NT. We plug the number into the formula. Notice that P is the unknown. So we need to solve for P by dividing both sides with whatever this number is. Because it's multiplied to P, we just divide by the entire number on both sides of the equation. So that gets P by itself because this quantity cancels with this quantity. So we've solved for P. So technically we found a solution. The only thing left is to enter all numbers, remember all numbers, into the calculator. Just at the same time, make sure you have parentheses when you go divided by parentheses to the exponent parentheses 12 times 4 depending on your calculator, and hit the enter button once, and that gives you the final answer. Now notice that this is a special type of account. The first 10 years, the account has a certain interest rate described here. And then for the next 8 years, the account has a different interest rate as described here. So there are two different interest rates at two different periods of time. So that is what is different about this account. So what happens for the first 10 years? The amount deposited is 6,000. The rate is 0.0525. The time is first 10 years, so time is 10. N is 2 because semi-annually would mean half yearly, which is twice a year. We need to figure out A. So what is the accumulated amount after 10 years? And that is what we have here. So after 10 years, what we have in the account is 10,074.29475, and I've left all the decimal places for a reason. So now this amount, it's not the original amount, so the money has grown, and this amount is deposited into a second type of account for the next 8 years. So that makes it a total of 18 years. 10 plus 8, 18. So the principal now is the amount that we deposit into this account at the beginning of the time period of 8 years. So that is the answer that we get from the previous step. Rate is 0.054. That's the interest rate in the new account. And it's compounded quarterly. If it's quarterly, then it is 4 times a year. And the time is 8 years. So plugging in all the numbers into the formula again, A equals P times 1 plus R over N whole to the NT, we get 15,473.01. So I do the rounding only at the end, and that gives me my final answer. So if I start off with $6,000, after the money goes through 18 years in 2 different types of accounts, the total accumulated amount after 10 plus 8, 18 years is 15,473 and 1 cent. Now, look at the next problem. A 30-year-old worker plans to retire at the age of 65. So he's 30, he'll retire at 65. So that's he's going to be retiring in 35 years. He believes that 500,000 is needed to retire comfortably. So that's his goal. So his goal is to make $500,000 in the next 35 years. How much money would he have to put into his account now, which means what is P? What we deposit now is the present value, so that's P, at 7%, and then we know it's compounding monthly, which would mean 12 times a year to meet his goal. So we have all the numbers. So the time frame is 35 years because he's 30 now and he wants his money to be in the account for the next 35 years. So that makes it 35. R equals 0.07, that's the rate, interest rate. N is a monthly compounding situation, so N is equal to 12. His goal, that is the amount he wants to withdraw from the account at the end of 35 years, is 500,000. So P equals, what we need to figure out is the present value of the money, what we need to deposit now. So I just use the formula for P. It's 500,000 divided by 1 plus 0.07 divided by 12 to the 12 times 35. Plug it all into the calculator, and this is what we get. Make sure you're not doing the calculations in bits and pieces. Just enter everything into the calculator and hit the enter button once, only once. So what this calculation tells us that if we deposit $43,455.01 into the account today at 7% compounded monthly, in 35 years, what we're going to have is $500,000. Now suppose an investment is compounded n times a year, and it has a nominal interest rate of R. It is in the decimal form, and R is always in the decimal form. So we need to figure out the yield percent. What is the yield percent? So if we were to put this exact same amount into a simple interest account, then what would be the simple interest rate on this account that is equivalent to the compound interest rate R compounded n times a year? So the yield is just the simple interest rate that would get us the same returns as the compound interest rate that is given to us. So if we need to find yield, this is the formula that we use. Usually the yield formula is used to compare two different types of compound interest accounts. Um, if we had a choice of putting our money into two different types of compound interest accounts, it is sometimes hard to tell which one is a better deal. So reducing both to the yield percent gives us a standard form of percent, which will help us compare the two amounts. So whenever in any situation, in any problem, we need to compare um, uh, two different types of accounts and figure out which is a better deal, it is always a good idea to use the yield formula, y equals 1 plus r over n whole to the n minus 1. So the yield formula is always used when comparing two types of accounts. So what are the two types of accounts that we have here? It says find the annual percent yield for each type of investment to select the better of the two investments. So we have 5% compounded monthly, 5.25% compounded quarterly. So look at the first account. Rate is 0.05. Monthly compounding suggests n equals 12. Plug in the numbers into the yield formula, and we get basically enter all the numbers into your calculator and get 5.12%. So 5.12% is the simple interest rate that will give us the same returns as a 5% interest rate compounded monthly. Now let's compare this to the second account. So in the second account, the percentage rate is 5.25%, which is 0.0525. Compounded quarterly would suggest n equals 4. Find the yield percent by plugging in all the numbers into the formula. Use your calculator. Don't do these calculations in pieces. Use the functions of the calculator well without having to do any extra work. Plug in all the numbers, hit enter, and then you get 5.35%. So when we examine the two accounts, 5% compounded monthly versus 5.25% compounded quarterly, more compounding is better. So we cannot say that compounding monthly is better because here the rate is higher. So when we are in that sort of a confusion, that is when we use the yield formula to decide which is a better deal. Now, clearly, the yield percent for the second account is better than the yield percent of the first account. This tells us that first one or the second one is a better deal. So this is what we're going to pick if we had a choice. Now let's look at the next problem. The question says, you have a certain amount of money to invest, $3,700,000, in an account paying 3.75% interest compounded semi-annually and an account paying 3.65% compounded daily. Which type of investment is better? So here, again, the problem boils down to comparing two types of compound interest accounts. Now, does it really matter what amount you're investing when all you have to do is figure out which is a better deal? So when figuring out a better deal, it really doesn't matter whether you're investing $1 or you're investing $3,700,000. So this information is really not used if you think about it, because all we're going to do is use the yield formula for each one of these types of accounts, figure out the yield percent for each one of these accounts. So all we do is compare the yield percents and figure out which is a better deal. Now, another way, which would be a little more messy, would be to actually figure out um, what the accumulated amount is for this amount, let's say in a couple of years or 3 years. So we could do that and see which uh, account gives us a greater accumulated amount of money, but it's just a little messier. In our calculations here, we didn't use this large amount, 3,700,000, because we didn't really need to. Our job was to just compare the two accounts and decide which one was the better deal.